Okay, so we started chapter number 3 last week. So did anybody go through the material which we covered, and anybody have issues regarding anything? Please feel free to ask. Did anybody go through the material? Anybody have any issues? Are you catching up with me? I need a response, yes or no or something.
Yes, sir.
If
Yes,
if
sir.
if if,
No,
if,
sir,
if you
there were
feel,
no issues.
sorry.
I was saying that there were no issues in the previous lecture.
Okay, that's good. Because once again, I tell my students again and again, if you feel any issue, don't hesitate to ask me. Okay, let me know where you do not understand something. It's my responsibility to make you understand things. Okay, so don't worry about that. So, anyways, I'm going to just summarize the material which we covered last time, and so that we can continue forward with it. Okay. So we were discussing about the property diagrams, and basically we were discussing about the phase change process in pure substances. And the main phase change process of our concern is not between solid and liquid. The solidification or melting is not our concern. Okay, our concern was vaporization or condensation. Okay, so we have liquid. Okay, it's initially in the compressed liquid region. It's initially in the compressed liquid or subcooled liquid state, and we what we do is that we heat the liquid. Okay, and if the temperature of the liquid is increasing, this is an indication that it is in the compressed liquid or subcooled liquid state. Okay, and then it comes to a state that if you further heat it, then instead of raising the temperature, it will start converting into vapor. And this is the point that we say that it is now saturated liquid. Okay, so after that, we further heat the liquid, and then temperature remains constant. But what happens is that the phase change process continues. So the liquid is being converted into vapor. So that's the vaporization process which is taking place. So this is known as the saturated liquid vapor mixture process region. Okay, and in this region you'll have the liquid and the vapor both present at the same time. Okay, the process is going to continue if you further heat it up, and we will reach a state that all the liquid, even the last drop of the liquid, has been converted into vapor, and now this is saturated vapor. How do we know it is saturated vapor? If we cool it a little slightly, then part of the vapor will convert into liquid, so it's ready to condense. That's why it is known as saturated vapor. Then now it is saturated vapor. Then if we further heat it up, now the vapor is going to expand more, and the temperature of the vapor is now going to increase. Okay, so this is known as the superheated vapor region. How do we know that the vapor is superheated? That if we cool it, its temperature will go down, but it will not condense into liquid. So these were the states that we discussed about the phase change process from liquid to vapor. And then we discussed that this phase change process takes place at different pressures. Okay, so if we keep on increasing the pressure, the trend would remain the same, but what will happen is that the curve is going to shift up and up over the TV diagram. Okay, and then we discussed that if we keep on increasing pressure, uh, the the saturated liquid vapor mixture region keeps on decreasing, and a time comes when the saturated vapor and saturated liquid points becomes one, and that is the critical point when there is no saturation region. So it's just one point, which is known as the critical point. Beyond critical point, if we further increase the pressure, that's the supercritical pressure we call it, and this is the point where it's hard to determine whether whether the pure substance is in the liquid state or is in the vapor state. So it's like in a state where it's really hard to determine. So there is no direct way of determining whether it is in the liquid state or the vapor state. Anyways, we will focus our study in this course to subcritical pressures, to subcritical points, not supercritical. So we're not going to move beyond supercritical, beyond critical point. If we draw all the saturated liquid points for all different pressures and all the saturated vapor points for all different pressures, okay, we're going to make two lines. One line is the saturated liquid line, other will be the saturated vapor line, and these two lines are going to meet at one point, which is the critical point. And if you look at it in the diagram, it's going to look like a dome. So we'll have this dome in front of us. Inside the dome, we'll have the saturated liquid vapor region. The top point of the dome is the critical point. The left-hand side of the line of this dome is the saturated liquid line. The right-hand side line of this dome is the saturated vapor line. Okay, the right-hand side of this dome is superheated vapor region, and the left-hand side of the dome is the compressed liquid region or the subcooled liquid region. So this was the TV diagram that we discussed for the pure substances. Okay, this is going to be the same for any pure substance. Basically the main pure substances that we are going to focus in this course will be steam or water, you can say, and a refrigerant R134A. Then we also discussed that this is a TV diagram. We can also have a PV diagram, and we said that temperature and pressure have an opposite relationship with respect to the specific volume. Okay, so the TV diagram and the PV diagram are very similar in nature, except for the fact that in case of the TV diagram, the constant pressure lines are like moving upward from compressed liquid region to saturated vapor region. They're like moving up. And in case of the PV diagram, the constant temperature lines are like moving downward. So if you keep on increasing if you keep on increasing the pressure, so what's happened is that the volume is going to decrease. So anyways, this is the PV diagram and the TV diagram, property diagrams of the pure substances. Then we discussed about the extended diagrams, where we can also include the solid phase, but I told you that you just need to memorize these diagrams. We are not going to use them in calculations. They're just for your knowledge. Okay, so we talked about PV diagrams for the case of substance that contracts on freezing, or for the case of substance that expands on freezing, such as water. We also talked about the PT diagram. Again, for the PT diagram, I told you that it's something that's not much of our concern, but you should know this diagram. Okay, you should know all the points, all the lines, the process of sublimation, at least the definition. What does sublimation means? Triple point. I don't want you to memorize the temperature and the pressure values, but at least you should know that what is triple point in general. Triple point pressure and temperature, a substance exists in three phases in equilibrium. So all the three phases are going to be there in equilibrium at that point. Okay, so you should know all these diagrams. Okay, then there was a PVT surface diagram, but this is just for a presentation. If you want to go through it yourself, you can go through it. Not significant for our concern. So this was just the summary of what we did last time in chapter number 3. Now we're going to move forward from here, okay, and we're going to start studying the property tables. Okay, so before actually starting this thing, anybody have any question you can ask? So far everything is clear?
Yes, sir.
Okay, thank you. Okay, now let's discuss about the property tables. Some property tables are going to be very important for this course, and you're going to use the property tables from here onward till like the last lecture. So you're in week number 4. So we are introducing the property tables in week number 4, and then from week number 4 till week number 16, or till whatever week we continue, we're gonna use these tables throughout. Okay. Now let's first discuss that what this property table represents. Okay, there are different kind of tables in it. Okay, the tables are numbered. We're going to go through them. Okay, so let's first discuss the parameters which are there within these tables. For example, look here. This is saturated water temperature table. Okay, now by looking at by looking at these words, you can actually judge that what this table is about. For example, here it is saturated water. So we're talking about saturated water, okay? And what is the fluid? It is water. And what kind of table it is? It is temperature table. Temperature table means on the first column is the temperature column, and corresponding to that column, all other properties are given. Is this thing clear? I want your responses all the time, okay? So please keep your mic in a position where you can answer me, okay? So far it's clear, okay?
Yes, sir.
Okay. So against the temperature, now let's look at what are the properties that we have. Okay, the first thing is that against the temperature we have saturation pressure. Okay, is given in kilopascal. But again, I told you that you need to know the conversion between kilopascal, megapascal, bar, atmosphere, because these things are interchangeably used throughout the tables. Okay, so anyways, the temperature is given in degrees centigrade. Okay, then after that we have the column for the specific volume unit, meter cube per kg. Okay, we have the specific volume. Whenever it's written F means for saturated liquid. Whenever it is written G means saturated vapor. G means gas, F means fluid. So VF means saturated liquid, VG means saturated vapor. So what is the specific volume? Specific volume symbol is V. So VF, whatever the value we have here, that's VF. Then its unit is in meter cube per kg. Then we have VG, its unit is in also meter cube per kg. So specific volume for, let's say, water at 0.01 degree centigrade is 206 meter cube per kg. Okay. Then the next column what we have is the internal energy. Internal energy we represent by U. Okay, it's a specific internal energy actually. So it's basically kilojoule per kg. So you have UF value. Okay, what the internal energy of the specific internal energy of the fluid, saturated liquid. Okay, so then we have here UG. Okay, and in between we have UFG. Now, what is UFG? UFG is just the difference between UG and UF. So if you subtract UG minus UF, is going to give us UFG. So UFG is equals to UG minus UF. As simple as that. Nothing complicated. Yes? Anybody was asking something?
Yes, sir.
Yeah.
कोई difference है if we write UFG or UGF? Yeah, is it just the difference in
actually, normally it is written UFG. So it's better you use the same symbol, otherwise you're going to confuse yourself. Otherwise, there's not a big difference. Okay, so UFG, when we write it, it means UG minus UF. Okay, and this is the same symbology. This is the same symbols which is being used throughout the book. So it's again random. There is no specific reason for putting UFG or UGF, but the thing is that in order that you do not confuse yourself, since we are using the same textbook. So
what I meant to ask was if we write UGF, will it change to UF minus UG, or does it not matter?
It does not matter. It does not matter. The only thing is that UFG means difference between UG and UF. That's it. Okay, what's the
Yeah.
absolute difference? What's the absolute difference? So greater value minus a smaller value, you can say that. Okay. So here we have UFG. Okay. Again, you can check here as well. Like for example, if you subtract 2381.8 from 2381.8, subtract 21.019, you're going to get 2360.8. So it's kind of I don't know. You might say that I can do this calculation myself. What was the point of putting this in the table? But okay, to make your life easy, maybe a little. Okay. So, but UFG, it's only means UG minus UF. Okay. So this is what it means. Then we have another property here, enthalpy. Okay, we're going to discuss about enthalpy in a moment after that. Okay, but just consider it here. There's a property enthalpy. It's kilojoule per kg. Okay, it's again a form of energy. Okay, and it's represented by H. So its HF value is the enthalpy at this specific temperature for saturated liquid. The enthalpy at this specific temperature for saturated vapor. Okay, and then HFG is what? Hg minus HF. As simple as that. Nothing more. So subtract HF value is subtract HF value from Hg value. Okay, you're gonna get this thing, HFG. So 2510.1 minus 21.020 is gonna get 2489.1. Okay. Similarly, then we have another property here, entropy. Entropy's unit is kilojoule per kg Kelvin. We're going to discuss this property in detail in second law of thermodynamics, specifically when we're going to start chapter number 7. So right now, just take this property for granted. We're going to understand it much better when we reach there. Okay. So anyways, the property values are given here. SF is the entropy. Its symbol is S. It's the entropy is given for saturated liquid, SF. Okay, then we have SG is for saturated vapor, entropy for saturated vapor, and SFG is what? SG minus SF. That's it. So if you subtract 0.0763 from 9.0249, you're going to get 8.9487. Okay. So it's important to understand what are the different values you can get from this table. Okay. So that we might be able to use this table. So let me summarize it. This table is of saturated water. How do we know it's saturated water? Look here, it's written saturated. And how do we know it's water? Look here, it is written water. This is temperature table. Why we say it is temperature table? Because the first column is the temperature, and corresponding to temperature, all properties are given. Okay, what properties we have? Corresponding to temperature, we have saturation pressure, we have a specific volume for saturated liquid and vapor, we have internal energy for liquid, vapor, and their difference, we have enthalpy for liquid, vapor, saturated vapor, and their difference, we have entropy for saturated liquid, saturated vapor, and their difference. Okay, these are the values which are provided in the table. Okay. So before moving forward, first of all, do you understand this? Is there anything in here which you do not understand? Please feel free to ask. Everything is clear so far?
Yes, sir.
Yes, sir.
Okay, good. So let's move ahead. Okay, let's discuss about these two terms. We are not going to discuss in a lot of detail right now here, but anyways, let's discuss about these two terms, enthalpy. Now, enthalpy is basically a term for useful energy. Okay, let me give you an understanding about enthalpy. Okay, look, for example, you have water, and the water is at let's say boiling water, 100 degrees centigrade. Temperature is 100 degrees centigrade. The water is boiling. One can tell this water has a lot of energy. If I put my hand into water, it will burn. So because there is a lot of energy in water. So one thing is very clear. The temperature represents the internal energy of the water. Okay. So the water can can do some work, can do some damage, can do some useful work. Something is could be done if we have a lot of internal energy inside water, and that internal energy could be represented in the form of temperature. So high temperature water is an indication that water has a lot of energy. So this thing is clear. This thing, anybody can understand this thing, okay? But let's talk about something else. Suppose if you go to car wash, let's say to car cleaning services, to car wash for car maintenance, you see there the guy has a pipe. From the pipe he is putting pressurized water on the car and cleaning the car. Now the water there is not at 100 degrees centigrade. It's not heated water, but the pressure of the water is so much that it does a lot of work. It cleans your car, okay, and it does a lot of work. And if you just touch that water, you're going to realize that that water had a lot of pressure, but its temperature is not high. Okay, so it's same like the ambient temperature, whatever the outside temperature is, almost similar to the temperature of the water. So this means that temperature is not just the only thing which compasses or which signifies the inside energy of water. There could be other form of the useful energy inside water, which is not temperature, rather which is pressure. Okay, so now if we want to say that what is the total amount of useful energy inside water, okay, we cannot just signify it with temperature, but we will also have to signify it with pressure. And the pressure is something that can do some work. Pressure is something that can do some work, and work has a unit of energy. Okay, and when we signify water temperature, we represent it in the form of internal energy. So let's combine the two energies of the pressure and energy of an internal energy of the pressure and internal energy, and let's give it a new name. We call it enthalpy. Okay, so enthalpy is basically what? It's the useful energy content of any fluid, useful energy content. And we do understand that the useful energy content could be because of two reasons. One might be that the substance has a lot of internal energy, so its temperature is very high. But there is another possibility that the temperature is not high, but the pressure of that substance is very high. So we can see that the water, which is not very high pressure, but temperature is very high, let's say boiling water, can do some work. But at the same time, water which is not at a very high temperature, but very high pressure, as you go to see in car cleaning, okay? So this pressurized water can do the cleaning of the car. So it can also do some work, okay? So this is also a form of energy which is inside the water. Okay, so combine these two forms of energy, we say that the total useful energy of any pure substance is its enthalpy. Do you understand the concept of enthalpy right now or not?
Yes, sir.
Okay, good. Anybody have any question you can ask? Actually, I have opened the slide on my screen. So if anybody is sending me on chat, so I cannot really see the chat. So
Sir,
yes.
sir, can you please repeat the enthalpy thing that is?
Okay, once again. Okay, so enthalpy is basically what? It's the total useful energy of the fluid. Total useful energy of the fluid. Now, the point is that if I have water, okay, how can I say that the water has a lot of energy? Okay, so let's say the temperature of the water is high. Let's say the water is boiling. Boiling water can do a lot of work. Okay, you put your hand into the boiling water, it's going to burn your hand. Okay, so burning the hand is utilizing the energy to do some work. Okay, so boiling water has basically the ability to do the work. And how do you know that the water has a lot of energy? Because the water is boiling, its temperature is high, so we can say that the internal energy of the water is high. So this is one form of energy that we know. inside the water. Okay, but let's talk about another form of energy. Okay, suppose if you go for a car wash, you can see that the water they are throwing on car, they're putting on car is at a very high pressure. Okay, from a nozzle at a very high pressure, water is being water is being used to clean the car. Okay, so they make the water jet. If you put your hand in the water jet, you're going to feel a lot of pressure of water, but you will feel that the temperature of the water is still normal temperature. It's not hot water. Okay, so what does it mean? It means the water is not hot, its temperature is not high. That means internal energy is not high, but there is some other form of energy inside water as well, which can do a lot of work, and that is the pressure energy. Okay, so if we want to specify the total useful energy, it will not just be the internal energy which is responsible to which could be signified by temperature, but it has to be another form of energy as well, which is pressure, because if the water has high pressure, it can also do a lot of useful work. So let's combine these two forms of energy. Let's combine these two forms of energy and give it a new name. And let's call it enthalpy. So enthalpy is a combination of internal energy. If the internal energy is high, temperature is going to be high, and it has the capacity to do some work. At the same time, there's also pressure energy. Okay, so pressure energy, if the pressure of the water is high, this is also the water has high energy and has the capability to do some work. So if we add these two energies, the energy because of the pressure, the energy because of the internal energy, we give it a new name, we call it enthalpy. So enthalpy is the total useful energy content. Just by specifying the temperature, internal energy, we cannot really say that the water has high energy or low energy. We also have to specify what is the pressure of the water, because the pressure itself has the capability to do a lot of work as well. Okay, so this is the concept of enthalpy. Enthalpy is a terminology defined to signify the useful content of any pure substance. Do you understand now?
Yes, yes.
Okay, so as I mentioned you here, you can look here. The enthalpy is H, capital H, is equals to internal energy plus energy due to pressure. Now, energy due to pressure is basically what? Pressure multiplied by the volume. Okay, if you multiply pressure and the volume, you're going to get the units of energy. Okay, so pressure is something which is going to change the volume. Okay, so this is how pressure multiplied by the volume transforms into work, which is a form of energy, which will be there inside the fluid. So if you write in the specific terms, so it will be small h is equals to small u plus p multiplied by specific volume. So this will be kilojoule per kg, and this is the enthalpy. Okay, enthalpy is a very important parameter, and we will be using this parameter a lot in our calculations. If enthalpy is clear, then I can move towards entropy. Is there anybody who have any question? Feel free to ask. Okay, no problem. If anybody don't understand, I can repeat again. Everything is clear so far?
Yes, everything's clear.
Okay. The next thing is entropy. Now, entropy is something we're going to discuss in a lot of detail from chapter number 6 onward. So specifically, chapter number 7 is all about entropy. Okay. So right now, just consider that entropy is a property associated with second law of thermodynamics, and we will define it later. Right now, we do not want to enter into the discussion of entropy because it's going to be a huge discussion. Okay. So right now our objective is just to learn the thermodynamic tables, to see how to use the thermodynamic tables. Okay, so entropy is just a property. Right now it's a thermodynamic property. Okay, its unit is kilojoule per Kelvin, or the specific entropy will be kilojoule per kg Kelvin. Okay, so just know this thing for now. When we move towards chapter number 7, you're going to understand this property in a bit more detail. Okay, so let's move ahead. Okay, now let's talk about the different types of table that we have. Okay, so we have in your textbook, we have the tables in the SI units as well as in the English units. But again, as I told you, that we will be focusing ourselves over the SI units, so we will not be using the English units tables. I have also provided you the thermodynamic table separately in the folder of textbook on the Google Classroom. Okay, this tables is from the book, from the same textbook that we are using. Okay, and let's discuss that what kind of tables do we have. Okay, so you saw the example before, and that was about saturated water temperature table. Like, so that is basically table A4. Okay, so right now what I do is that I start sharing the other file. Let me stop sharing this one. Okay, and, okay, can you see on your screen the file for the thermodynamic property tables and charts in SI units?
Yes, sir.
Okay.
Yes.
Okay, so you can see here I've written here that it's taken from the same our textbook, 5th edition, extracted from pages 883 to 932, all the whole thermodynamic tables. Okay, so let's have a look at it. At what kind of tables do we have in here? Okay, so we have table A1. Table A1 is going to discuss about the molar mass, gas constants, critical point properties. We're going to go and look into it. A2 is about the ideal gas specific heats. Okay, A3 is about the properties of common fluids, solids, and foods. From A4 onward, we start with the main tables. The saturated water temperature table, which you saw there in the lecture slide. Okay, that's table A4. Table A5 is again saturated water, but this is not temperature table, this is pressure table. Means the first column will be the pressure instead of temperature. And all the properties will be again for saturated water, but will be corresponding to to whatever the pressure that we are discussing about. Okay. Then we have table A6, that is for the superheated water. Suppose if the water is in the superheated region, then the table is A6. Table A7 is basically for compressed liquid water or subcooled liquid water. Okay. Table A8 is for saturated ice water vapor. But since it's talking about ice and water vapor, so this is not the table that we are going to use. So that this table will not be much in our use. Then table A9 is the TS diagram for water. Okay, table A10 is the molar. So we have figure A9 and figure A10. So it's a molar diagram for water. This is also something we are not going to use it. These are alternate to the tables. So we will focus ourselves over the tables. So here from table A4 to table A7 are the ones which are of significance regarding water. Okay, then we have another fluid which is R134A. Okay, again the same kind of tables that we have. We have saturated R134A temperature table. This will be important for us. And then we have saturated R134A pressure table. This will again be important for us. Then superheated refrigerant R134A. This will again be important for us. So we will have these three tables which will be important for us. The pH diagram is again an alternate to the tables, but we are not going to focus over that diagram. So this is not something we are going to work on it. Then figure A15 and figure A15 is basically a Nelson-Obert generalized compressibility chart. We are going to study inshallah in this chapter. Okay, so I have provided separate charts for it as well. So we're going to work on that. So this will be important. Properties of atmosphere at high altitude, you might use it. Okay. Then we have ideal gas properties. Now, ideal gas properties of air, table A17 will be very important table, but not for now. It will be basically for chapter 9. Chapter 9 will be totally focused over this one, ideal gas properties of air. Okay, then we have ideal gas properties of nitrogen, oxygen. They are not really important for us. Carbon dioxide, carbon. Okay, these are basically, if we were doing chapter number 15, then these tables would be important, but since we will not be doing them, okay, so these tables will not be important for us. Okay, so carbon dioxide, carbon monoxide, hydrogen, water, atomic. Again, then enthalpy of formation, Gibbs function is also not important for us. So anyways, I think after this, yeah, no more, nothing else important. Okay, so this whole is not important. Okay, so our focus will be over on only on these tables which I have mentioned you. Table A1, A2, A3, A4, A5, A6, A7. Then we will have table A11, A12, A13. Then we have table figure A15. Then table A17. So these are the tables which will be important for us throughout our course. We will be using these tables. The rest of the tables are something which we are not going to use it, since we are not going to cover those chapters. Okay, so let's move over to one by one. Because this chapter is about thermodynamic tables, so we're going to spend some time and study those tables. Okay. So table A1, you can see here, what do we have in table A1? We have molar mass, gas constant, critical point properties. Okay, now you know what is critical point. Okay, we discussed about the critical point in the phase diagram or the property diagrams. So we have for different for different substances. You see here, air, ammonia, argon, benzene, bromine, carbon monoxide, chlorine, ethane. So many different kind of gases. Okay, oxygen, propane. In the end, you have water, and then we have xenon. Okay, so their formula is given. Okay, their molar mass is given, kilojoule per kilomole. The gas constant R, gas constant is given, kilojoule per kg, Kelvin. Okay, these values are given. Then what do we have here for critical point properties? Critical temperature, critical pressure, critical volume. Okay, so the critical point properties are given. Okay, so for these gases, okay, whether it is air, ammonia, all of the properties, and these are given. For example, temperature is given in Kelvin. Now you see here, sometimes temperature is given in degrees centigrade in the table, sometimes it's given in the Kelvin. Look here, the pressure is given in megapascal, sometimes it's given in kilopascal. So you always need to look into the table, and you look at the unit of the parameter. Okay, so if you are in a specific table and you're actually reading a value from the table, then you need to look at what is the unit of the value which you are reading. Okay, so that you know that what unit you are actually utilizing this value. Okay, then we have a specific volume. The specific volume is in meter cube per kilomole, not kg. The specific volume is there. So these properties are given for all these gases. Okay, and the unit kilojoule per kg Kelvin is equivalent to kilopascal meter cube per kg Kelvin. Okay, the gas constant Ru is the universal gas constant, and this value is also there in the table. Most of the time students forget this value. Okay, and they ask the doctor, please provide the universal gas constant value, although this value is there in the table as well, but it's not given separately. It's given at the bottom of table A1. So Ru is a universal gas constant. It is 8.31447 kilojoule per kilomole Kelvin. M is the molar mass. Okay, so that's about table A1. Anybody have anything to ask regarding table A1? Okay, everything is clear so far?
Yes, sir.
Okay, then we move towards table A2. In table A2, we have the gas properties. You see all these gases, their formulas are given. Gas constant is again given. Then you have the Cp value, you have the Cv value. Okay, what are these values? We're going to discuss in chapter number 4, inshallah. Okay, but anyways, you should know that these values are there. Okay, and the K value. Okay, so I'm not discussing about these values here. What do they mean? But we are going to discuss them in chapter number 4, inshallah. Okay, so anyways, but these values are provided for these gases at a specific temperature. What temperature it is? 300 Kelvin. Okay. Now suppose if the temperature is not 300 Kelvin, then for some specific gases, if the temperature is varying, the Cp and Cv and K value might also vary. So for example, for air, if the temperature is varying from 250 to 1000 Kelvin, then the Cp, Cv, and K values are provided, okay, at different temperatures. Similarly for carbon dioxide, similarly for carbon monoxide, for hydrogen, nitrogen, oxygen, okay. So then we have here Cp as a function of temperature. But anyways, this part C of this table is something we are not going to use, okay, because this is normally used in the software. You can apply it in the software, okay. You have the formula, you will be using the software obviously, but this is for your own practice if you want to do it, okay. So these are the constants here. If you know what is the temperature in Kelvin, okay, you can actually find, if you just substitute those constant values, you can actually determine what is the average Cp value as a function of temperature. So we have this table as well. But anyways, for paper-based exam, this will not be important. Okay, so you will be using these table A2B and table A2A. Table A2A is at a specific temperature, and table A2B is for varying temperature for some of the gases. Okay, then we move towards table A3. Table A3 is the same values, properties of common liquids, solids, and foods. So those were for the gases before. Now this is for different liquids, solids, and foods. So we have ammonia, argon, benzene. We have boiling data. We have freezing data. We have liquid properties. Liquid properties basically are the ones which are more important for us: specific heat, density, temperature. Okay. So we have freezing data. We have boiling data. For different kind of fluids, okay, and this is part B of the table A3. Okay, here we have the metals. That means now we have entered to solids. Okay, so we have different kind of metals at different temperatures, properties. Okay, then we have asphalt. We have non-metals here. These properties are there for them. Then we have some, instead of having metals, non-metals, we have organic materials. Like we have apples, bananas, beef, butter. These properties are there. Anyways, this is not something we're going to use much. Maybe in one or two problems you might need to get some values from here, but not too much. At least you should know that this thing is there. The tables will be there with you throughout your exams, throughout the semester. So at least you should know, okay, these values are there with you. Suppose if you want to use it. The table A4 is something that I showed you, right? In the slide, we have table A4. Okay, till table A3, so far everything is clear. Everything is okay so far? I need an answer.
Yes, sir.
Okay. Okay, table A4, I showed you the table. Table A4 in the slide, it was only the first two lines were shown. But anyways, this is a big table. So you have all these properties that we discussed, okay? And then these properties are there for different values of temperature. This is saturated water temperature table, okay? And so we have temperatures in degrees centigrade for 0.01, then 5, 10, 15, 20, and so far. It's going to continue. Table A4 continue here. So this is for water. Then table A5 is for saturated water, but this is pressure table because the first column is the pressure. And corresponding to this first column, all other properties are given. So we'll have saturation temperature and then the specific volume. Then we have the internal energies, we have enthalpy, we have entropy, all these properties. The same properties are provided, but corresponding to the pressure. Okay, so corresponding to different pressures, you have all these properties available with you. So this is saturated water pressure table. So you can see here the pressures are in kilopascal. And we're going to continue this table, table A5. till here. Then we have table A6. A6 have superheated values, because for table A6, when we talk about superheated water, so you don't have F and G values now. So you have everything vapor. So you have different pressures. So let's say at this pressure, you have different varying temperatures, and corresponding to a specific temperature and pressure, you can find specific volume, and internal energy, enthalpy, entropy. If the pressure change, let's say you have, instead of 0.01 megapascal, you have, let's say, 0.05 megapascal, then all these properties are here against the temperatures. Then for different pressures, you have, this is superheated water table. It's going to continue. Next page, then third page, then fourth page, then fifth page, 5 pages of the table for superheated. No, sorry, 4 pages. It's finished here. Then we have table A7, which is the compressed liquid water. Again, for compressed liquid water, we know everything is liquid, so no F and G values. We have just specific volume, U, H, S, against temperatures for different pressures. Okay, so we have table A7. This is just 1 page here. Table A8, I told you it's not of much significance for us. This figure A9 also, we're not going to focus on that, or figure A10. Okay. So from here onward, now the same tables which we saw for the case of water, now we'll have for refrigerant R134A. Okay. So table A11 is for saturated R134A temperature table. It's going to continue here. Then we have table A12, saturated R134A pressure table. All the properties of this refrigerant is given corresponding to the pressure in the first column. Then superheated refrigerant table, superheated R134A table, table A13. That's it. Then we have a pH diagram. We are not going to conserve. We're not going to focus on that. Then we have the Nelson-Obert charts. But if you see here, these charts are so small, it's really hard to get the values from these charts. So I have provided the bigger version of these charts. You see here, these are the bigger and the good version of the charts. Nelson-Obert chart, compressibility factor, Nelson-Obert charts. This is chart 1. This is chart 2. This is chart 3. So 3 charts for it. So they are provided to you. We're gonna use them. We're gonna discuss about them later in this chapter, inshallah. Okay, then we have table A16 is the properties of the atmosphere at high altitude. Okay, for at different altitude, what is the temperature, what is the pressure, what is the gravity, speed of sound. Anyways, this table is not really important for us, but we might use it somewhere. Okay, so table A17. Table A17 is very, very important, and we are going to focus in chapter number 9. Chapter number 9, this one table, which will be used a lot. Chapter 9. And chapter 9 is a very big chapter, and it's not an easy chapter, but only focused over one table. Ideal gas properties of air. So we have this 2 pages for ideal gas properties of air. Table A17, and that's it. From table A18 onward, none of it is important for us. Okay, so we are not going to cover those chapters where there is use of the rest of the tables. So this is step by step going through all the tables. I have shown you the thermodynamic tables. Okay, we're gonna be using these tables from this lecture onward till the last lecture. If anybody have any questions so far, please ask. Things are clear so far?
Yes, sir.
Okay. Let's stop presenting. Now present chapter 3. Okay. So we have properties of water. We discussed about this table. We have saturated water pressure table. We have superheated water table, compressed liquid. Okay. Then properties of refrigerant. We also discussed about that. Okay. So You want to have a break of 5 minutes and then we start back?
Yes, sir.
Okay, let's have a break of 5 minutes, and inshallah after that we are going to start back. Students, can you do one thing? In the chat box, please mark your attendance. Okay, just write present. So I will have a file of your attendance. I will update your attendance in the system. Okay, please write present in the chat box. uh, or instead of saying percentage, it's the fraction of the vapor within the mixture. Since we say that within the saturated liquid vapor mixture region, we will have both liquid and the vapor present at the same time. So we need to know that how much is the liquid and how much is the vapor content. So we define it by quality. So quality is basically what? It is mass of vapor by the total mass, or the fraction of vapor within the mixture. Okay, so if there is no vapor at all, means it is saturated liquid, then the quality will be 0. And if everything has been converted into vapor and there is no liquid at all, then the quality will be 1. So quality value is going to vary between 0 and 1. And within this mixture, within this liquid vapor mixture region, its value should be greater than 0 and less than 1. Okay, at saturated liquid, its value should be 0. At saturated vapor, its value should be 1. Okay, and in the superheated region, quality has no meaning. In the compressed liquid region, quality also have no meaning. So first of all, do you understand the concept of quality here?
Yes, sir.
The opposite of quality is we call it moisture. Moisture is opposite of quality. So when we say quality, quality is the fraction of the vapor content. When we say moisture, it is the fraction of liquid content. Okay, so let's say the moisture, we call it Y. Okay, so if the quality is 10, if the quality is 0.1, means 10%, 10% is the vapor, then the remaining 90% will be the liquid. So that means the moisture is 0.9. So if the quality is 0.1, then the moisture will be 0.9. Okay, so it's vice versa. So quality is basically moisture is not a parameter which we use significantly. Quality is the main parameter which we use throughout in this textbook. So this is something that you should know. Quality is the ratio of or the fraction of the vapor within this mixture. Minimum value can be 0, maximum value could be 1. When it is 0, saturated liquid. When it is 1, it is saturated vapor. Okay, or if it is within this mixture region, then its value should be between 0 and 1. It has no meaning in the compressed liquid or superheated vapor regions. Okay, now the question is that how do we determine the quality? Okay, so here you should understand one thing. There is a specific formula trend, you can say here. Suppose if you're talking about specific volume. So the trend is basically what? V is equals to Vf plus X Vfg. This is the formula. Okay, whether it is V, whether it is U, whether it is S, whether it is H. V, U, S, H. Whether it is enthalpy, entropy, internal energy, specific volume, it's the same trend. So we have V, whatever that property that we want to find is equals to Vf plus whatever there is a quality multiply by Vfg, which is Vg minus Vf. Okay, so suppose if you want to find out what is X, so X will be basically what? X will be V minus Vf divided by Vfg. Okay, this will be the X quality. So this is the trend that you have to use. This is the trend that you have to use. Okay, whether it is internal energy, whether it is enthalpy, whether it is entropy, it will be, or whether it is a specific volume. So it will be F value plus X multiplied by Fg. Okay, so is this formula clear?
Yes, sir.
You will understand it much better when we actually apply it in the numericals. Okay, now let's come over to the tables. Let me stop sharing this. Can you see the thermodynamic tables window here in front of you?
Yes, sir.
Yes, sir.
Okay, now let's come over to thermodynamic tables. Now suppose, now you need to focus with me, okay? This is something very important that I'm right now discussing with you. You know what? We need to have two properties. Suppose if we have two properties, the first thing that we need to do is we need to go into the saturation table and make a decision that, because based on the two properties, we need to make a decision that whether our fluid which we are considering is in which state. We don't know whether it is in the compressed liquid state, whether it is in the saturation state, or whether it is in the superheated state. So the first step always in the question is that if you have two properties, use the two properties to make a judgment. You need to make a decision that are you in the correct table? should you be in this table or should you go to some other table? Okay, so let me give you an example. Suppose you have a question where it is said that the pressure of the water is let me say here, it's 1000, okay, 1000 kilopascal, and it is said that the specific volume is point 0.18. Come on. Okay. Just a minute. V is equals to 0.18. So we have a situation here that we have water at 1000 kilopascal and with a specific volume of 0.18 meter cube per kg. Now the first thing is that we don't know whether under these two conditions the water is in the compressed liquid state, it is in the saturation state, or it is in the superheated state. So the first thing what we need to do is we need to go into the saturation table. Okay, since what we have is here is pressure, since the pressure is provided here, okay, so we are going to go into the pressure table, saturated water pressure table. Okay, so we're going to go into saturated water pressure table since the pressure is given here. Okay, now we're going to go to 1000 kilopascal. This is 1000 kilopascal. Okay, now corresponding to 1000 kilopascal, now what we need to do is we need to look at the specific volumes. Okay, so you see here, since the specific volume is given is 0.18. Okay, so now we need to look at the VF value and the VG value. Now what do you think? Is the V value which we have in our question is between VF and VG, or is less than VF, or is greater than VG? What do you think? 0.18. Do you think 0.18 is greater than 0.19, is less than 0.001, or is between 0.001 and 0.19?
Sir, less than
Less than what?
0.19.
Exactly. If it is less than 0.19, means it is in between 0.001 and 0.19. That means it is in between VF and VG. Make sense? If it is between VF and VG, that means we are in the saturation region. Between VF and VG is what? It's a saturation region, right? If you remember here, we have the diagram of saturation region. We have F values here, we have G values here, and if something is between G and F, that means something is in the saturation region. So that means this water at 1000 kilopascal and V equals to 0.18 is in the saturation region, means we are in the correct table. Do you understand this step or not?
Yes, sir.
Okay. Now tell me one thing. Suppose if I say that the value of V is not 0.18, rather if I say that the value is V is 0.2. Here, so V is 0.2. So what do you think? Are we in the saturation region now? We have to, how do we compare? We compare between VF and VG. Now VF is again at 1000 kilopascal, VF is 0.001, VG is 0.19. Our value of V is 0.2. So do you think 0.2 is greater than 0.19, less than 0.19, in between 0.01 and 0.19, or less than 0.001?
Greater.
is greater. If it is greater than G, means you are in which region? That means you are in the superheated region. That means if your pressure at 1000 kilopascal, if your specific volume is 0.2, means you are in the wrong table. You do not need to be in the saturation table. Now you have to move towards the superheated table. We make a decision, right? So the thing is that we had two properties, but based on the two properties, the first step is to go into the saturation table. And based on those two properties, now we need to make a decision. Are we in the correct table or should we change the table? Okay, so since here pressure and specific volume was given, so we went into saturated water pressure table. Corresponding to the pressure, we see the VF. Since we have the other property was V, so we see the VF and VG, and we compare the VF and VG value with the value of V that we have. And based upon that, if our value is greater than VG, we'll say that we are in the superheated region. If our value is between VF and VG, that means we are correct in the correct table. And suppose if the value of V was, suppose if the value of V was 0.0001. So suppose if the value of V was 0.0001. Then in that case, our value of V is actually even smaller than VF. So what does it mean? It means we are in the wrong table and we should be in the compressed liquid region. Do you understand here or not? This point is very important. You need to make a decision first, okay? And the decision is, you have two properties, but you don't know that based on these two properties, the water that you have is in which state. So you go into the saturation table and make a decision first. Are you in the correct table or should you change the table? If the value of the property that you have, when you compare it with the VF and VG values, if that value is greater than VG, means you're in the wrong table. You have to go to the superheated. If that value is between VF and VG, that means you are in the correct table. That is a saturation table. And if that value is less than VF, that means you are again in the wrong table. You have to move towards the compressed liquid table. Okay, this is the first step. Do you understand it or not? If anybody have any problem, please feel free to ask.
Understood, sir.
Anyone else? Anybody has any problem? Because it's very important that you understand how to use the table. Otherwise, all the rest of the course is going to become really a mess for you. Okay, you need to understand how to use the table. Okay, the same criteria is going to be used everywhere. Okay, so now let me give you, for example, let me ask you a question. Suppose if the pressure of the water is 1300 and H value, enthalpy, enthalpy is 700. Tell me, are we in the correct table or we not in the correct table? P is 1300, H is 700.
No, sir.
So if we are not in the correct table, then what should be the correct table? Should it be the superheated table or should it be the compressed liquid?
The compressed liquid.
Compressed liquid. Why? Because 700 is less than 814.59. You make a
Yes, sir.
decision. You have
Yes,
two
sir.
properties, and based on the two properties, you made a decision. Suppose if the value was not 700, suppose if the value was 7,000.
Then we would have been in superheated.
Superheated. Again, we were in the wrong table because it should be the superheated table. Okay. And if your value was, let's say, 1500.
Then we would have been in saturation region.
Saturation region. Why? Because 814 and 2786. 1500 is in between them. So that means we are in the correct table. Okay, so this is the main idea. Okay, you need to look at the two properties and then make a decision. Okay, now let me ask another question. Suppose the pressure is 1500, okay, and S is let's say 3. Are we in the correct table? S is
No, sir.
entropy, huh?
No, sir.
And why do you think we are not in the correct table?
Sir, because we have a greater value.
No, S is 3. Now look at the value that we have. At 1500, the value of S, the lower value is 2.3, higher
Okay.
value is 6.4. Our value is 3. Don't you think 3 is in between 2.3 and 6.4?
Oh, yes, sir. Sorry.
Okay. So we make a decision based upon the two parameters that we have. So we were in the correct table in this example.
Right,
Okay.
sir.
Okay. Let's give another example. Let's say this time use U. Okay. So P is 800 and U is 600. So what do you think? If P is 800 kilopascal and U is 600 kilojoule per kg, do you think the water is in the saturation region or not in the saturation region?
No, sir.
It's not in there. And why do you think it is that?
Because it's less than 800.
Because it is less than, no, not less than 800, because it is less than 719.97
Yeah,
UF.
sorry.
Okay? Because it is less than 719.97, so that means it is not in the saturation state. And if it is less than 719.97, that means it should be in which state?
Compress.
Compressed liquid. Perfect. Okay. So first of all, this decision making is very important. Do you understand this decision making or not? Is there anything anybody don't understand? Feel free to ask.
Understood, sir.
Anyone have any problem? Please ask. Okay. Okay, so now let's talk from the other perspective. Right now we were talking about from the perspective if the pressure is given and let's say we have specific volume or internal energy or enthalpy or entropy. Okay, let's talk about from the perspective of the temperature. Okay, suppose if the pressure is given and temperature is given. Okay, so in this case, we have to just compare it from the value of the saturation temperature that we have. Suppose, let's say, the temperature is, let's say that the pressure is 1000 and temperature is 200. Okay, so if you look here, for 1000 kilopascal, the saturation temperature is 179.88. Our temperature is higher than the saturation temperature. So when you compare the two temperatures here, when 200 is compared with 179.88, so our temperature is higher. Since our temperature is higher, that means we are in the wrong table. It should be the superheated table, right?
Yes.
And
Yes.
if let's say that the temperature was not 200, let's say if the temperature was 160. Okay, so again we are in the wrong table. Okay, because for at 1000 the saturation temperature is 179.88, our temperature is 160. That means we are in the wrong table and it should be the compressed liquid state.
Yes, sir.
You get it? So if you know the pressure, you can find out the temperature. Okay, if you know so if you know the pressure and any other property, okay, then you have to compare that other property with whatever the properties you have on the table, and you need to make a decision if you are in the correct table or if you need to move towards the different table. if this concept is clear so far, then I'm going to move ahead. Okay. So, but I really need to know if you understand it or not. If you don't understand it, feel free to ask. I'll be more than happy to explain again. Okay. Anybody, any problem? Are you catching up with me?
Yes, sir.
I'm hearing
Yes,
voice
sir.
of
Yes,
only
sir.
one student.
Yes, sir.
Okay. It's good. I need response from the other students as well. Okay. So I need to know that I'm teaching everybody. Okay. If this thing is clear, okay. Now let's move towards a different table. Let's say we move towards saturated. That was the saturated pressure table that we were discussing about. Let's go to saturated water temperature table. Now we will move towards saturated water temperature table if we have two properties, and among those two properties, one of the property is temperature. So suppose if the temperature is 250, okay, and internal energy is 1200. So what do you think now? Are we in the correct table or are we in the wrong table? Temperature 250 and internal energy 1200.
Sir, we might be in the wrong table.
Do you think our U value is not in between UF and UG?
Sir, table वही रहेगा. The table is right.
Table is right, right? Because our U value is 1200 and it is between UF and UG. Am I right?
Yes.
Yes.
So it was UF was 1080, UG is 2601. Our value is 1200. So it's between. So it's okay. It's supposed to be this one. The one who answered before, do you understand it?
Yes, sir. I thought it was 215, so I was looking at the
Oh,
upper one.
okay, okay.
That's fine.
It's okay. But you understand the concept. The
Yeah,
important
yeah.
thing is, okay. Okay. Now let's say that our T is 270, 270, and S is 2.2, 2.2. So our T is 270 and S is 2.2. What do you think? Are we in the correct table or are we in the wrong table?
Sir, we're in the wrong table.
We're in the wrong table because 2.2 is less than 2.9762. Which one should be the correct table? Compressed liquid or superheated?
Compress.
Compressed liquid. Perfect. Is it clear so far to everybody?
Yes, sir.
Okay, now you have to understand one thing here. Temperature and pressure goes against each other. So for all other properties, it's the same concept. If your value is greater than G value, then it's superheated. If your value is less than F value, then it is subcooled or compressed liquid. If your value is between F and G, that means you are in the saturation region. Okay. However, suppose if the temperature is given, let's talk about temperature is given as 205 okay, and the pressure is 1800. Okay, so what do you think? Temperature is 205, pressure is 1800. 205. Do you think we are in the correct table or wrong table?
It's a wrong table.
Wrong table. And our value of pressure is 1800. It's higher than 1724.3. So what do you think? Superheated or subcooled?
Superheated.
This is what I wanted to tell you, that for everything else it's okay, but when you are comparing pressure with pressure, this is pressure and this is pressure, right? You are comparing pressure with pressure. Whenever you are comparing pressure with pressure, the rules will change. It will become opposite. So 1800 greater than 1724.3 does not mean superheated. It means compressed liquid. This is only when you are comparing pressure with pressure. For rest of the things, it's same. Okay, so here when your pressure is 1800, which is greater than 1724.3, it means you are not in the superheated, you are in the compressed liquid region. This is only when you are comparing pressure with pressure. Okay, this is only this, so it goes opposite to every other thing. This when you are comparing pressure with pressure. Is this point clear?
Yes, sir. So, sir, what
Okay.
will happen in superheated? Like,
So suppose if the pressure was 1600. Okay, so when you compare pressure with pressure here, so 1600 is less than 1724.3, so that means it will not be compressed liquid, it will be superheated.
okay.
Okay,
Okay.
so this is only for one case, only for the pressure case. Okay, don't confuse it with the other cases. When you are comparing pressure with pressure, then the laws will become opposite. Greater than saturation will become compressed liquid, less than saturation will become superheated. But only for the pressure case, when you are comparing pressure with pressure. But for rest of the things, rest of the cases, it's the same way as I have mentioned you.
Okay, sir.
Okay, sir.
So far it's clear?
Yes, sir.
Okay. Suppose if you now you went through the table and you realize that, let's say you have to go into the superheated table. Then in superheated table is very simple. Like for example, in superheated table, you don't have F and G values. So let's say you're on the superheated water table, you know what is the temperature and you know, let's say what is the pressure. So corresponding to the temperature and pressure, you go and you find out whatever the property you need to find. Okay, so that's it. It's very simple in the superheated table. Okay, for the case of compressed liquid, there is one approximation. We're going to discuss about that approximation later. Right now, if this concept so far is clear with you, then I'm going to start sharing with you again the slides.
Yes, sir. All good.
Okay. Okay. So you see here, what's written here, superheated vapor. Superheated vapor is when your temperature is greater than saturation temperature, or your V is greater than VG, or U is greater than UG, or H is greater than HE. But only for the case of pressure, if you see here, it goes other way. P is less than P saturated, then superheated vapor. You see here? Is this thing clear now?
Yes, sir.
Okay, similarly when you have compressed liquid, okay, T less than T saturation, V less than VF, U less than UF, H less than HF, S less than SF. Okay, so for all the cases when it is less than the F value or saturation value, then it is compressed liquid. Only for the case of pressure, it goes the other way around. If P is greater than P saturation, then it is compressed liquid.
Okay, sir.
Okay, now here, okay, I'm going to discuss this thing later. Let's come over to a numerical, an example. Okay, find the internal energy of water at given states below. Okay, instead of sharing that one, let me share the screen with you now so that I can switch between the tables quickly. Share entire screen. Share. Okay. Can you see my screen?
Yes, sir.
Okay, good. Okay, now let's come here. Find the internal energy. So first of all, what do we need to find? We need to find internal energy, U, of water at the given states below for 6 megapascal. So pressure is given, 6 megapascal, and plot the states on the TV and PV diagram. Okay. So we have 5 cases and we need to find U. The first case is that we have set dry, saturated, or saturated vapor. They both mean the same thing. If it is saturated vapor or dry saturated and pressure is 6 megapascal, we need to find U. So what will be U in that case? Let's go into the table. Saturated water table. Pressure is given, right? So we're going to go into saturated water pressure table. And what was the pressure? Pressure was 6 megapascal. Okay. 6 megapascal means 6,000 kilopascal. Okay. So we have pressures in kilopascals. So we're going to go to 6,000 kilopascal. So 6,000, where is 6,000? Here it is. See here, this is 6,000 kilopascal. At 6,000 kilopascal, we need to find internal energy, U, internal energy for dry saturated vapor. Dry saturated or saturated vapor means we need to find UG. Right?
Yes,
So we
sir.
go into the table at 6,000. Okay. Let's try to figure out where it is. Where will be the U values? So that will be the UF. So not UF, sorry. That will be UG. Okay. So it will be 2589.9. So you can see here 2589.9. That's the answer of the first part. Is this thing clear?
Yes, sir.
Now, second thing is that we need to find wet saturated or saturated liquid means UF. Okay, so go into the table. So UF value will be 1205.8. Is it clear?
Yes, sir.
Okay, what is the third thing? Third thing is that moisture is 5%. I told you moisture is opposite to quality. If moisture is 5%, so what will be the quality? X will be 95% or 0.95. Is it clear? So we need to find X for X 0.95. If we need to find for X 0.95, that means we need to find U. We have to use this formula U equals to UF plus X UFG, where UFG is UG minus UF. So you know UG, you know UF, so that means you know UFG, you know UF, X is given, so you can find what is U. Is this thing clear?
Yes, sir.
Because we are talking about the same pressure. So for this same pressure, you know UG, you know UF, so that means you know UFG. UFG will be UG minus UF, and you know UF, you know X, so you can find what is U. So this is what's done here. So quality will be 0.95, and then U will be UF plus X UFG, so 1205.8 plus X. Or UFG value is directly provided in the table as well. Okay, they make the calculations for you. So 1384.1. So directly you can use the UFG value and you can find what is the U for this case. Is the point number 3 in the solution clear or not?
Yes, sir. Clear.
Okay, so next thing is basically what it is. Anybody have anything to ask? Please feel free to ask. Okay, for the next thing, it says that the pressure is 6 megapascal and temperature is 635 degrees centigrade. Okay, so now we have to compare temperature with temperature. Okay, so we go again to the pressure table at 6,000. What is the temperature? 275.59. And our temperature is how much? 635. So our temperature is greater than the saturation temperature. So we should be in the which state?
Superheated.
Superheated state. Perfect. Okay, so then you have to go into the superheated table. Okay, so let's move towards superheated table. Superheated table, this is superheated table. So we have 6 megapascal. So their values, pressure values are in megapascals. So let's go to 6 megapascal, 0.8, 1, 1.2, 2, 3.5. This is 6 megapascal. Okay, so this is 6 megapascal. Okay, and what is the temperature? 635. Now, do you see 635 here in the temperatures?
No, sir.
It's 600 is there and 700 is there, but 635 is not there. So what we're going to do is we're going to do mathematical linear interpolation. We're going to do is mathematical linear interpolation. Now there are multiple ways of doing linear interpolation. Okay, so it's up to you which methodology you want to use. But here the linear interpolation methodology that I have used is I'll show here. Okay, we need to find the u values, right? The u value is this column. Okay, so at 600 the u value is 3267.2. At 700 u value is 3453. Okay, so what I'm going to do is I'm going to write it like this. At 600, whatever the u value, at 700, whatever the u value, and I need to find at 635. This is the u value that I need to find. Okay, so I'm going to make this a small table here. Then what I'm going to do is that the smaller difference divided by the bigger difference means 635 minus 600 divided by 700 minus 600 is equals to smaller difference minus bigger difference. U minus 3267.2 divided by 3453 minus 3267.2. Okay, and this is going to give me the exact U value at 635. Is this interpolation clear? It's numerator over denominator equals to numerator over denominator. Smaller difference divided by bigger difference. 635 minus 600 divided by 700 minus 600 equals to u minus 3267.2 divided by 3453 minus 3267.2. Here you're going to make this equation and solve, and you're going to get the value of u at 635 degrees centigrade. This is linear interpolation. Do you understand how did we get the value of internal energy for 635 degrees centigrade and 6 megapascal?
Yes, sir.
This is linear interpolation. I use the linear interpolation by this way. If you want to use any other methodology, it's okay. It's up to you. You want to use any calculator or anything for it, it's okay. Is there anything which is not clear till here? Please ask.
Understood, sir.
Understood, sir.
Oh, good. I'm getting response from some other students as well. Okay. Okay, so let's discuss the last point. Okay, so last point is when the temperature is 100 degrees centigrade. So it's 6 megapascal, 100 degrees centigrade. Okay, so again we have to first move towards the saturation table. Okay, so first move towards saturation table. Okay, 6 megapascal, the temperature is how much? 275.59. Our temperature is 100. So what do you think, comparing temperature with temperature? Compressed
Wrong.
liquid, it should be compressed liquids. It is not saturated. Okay, so So what do we need to do is, now there are two ways. Okay, one way is that you move towards the compressed liquid table. This is the most accurate way. Okay, so you go into the compressed liquid table. So it's table A7, compressed liquid water table. Then corresponding to whatever the pressure and temperature you have, you can find what is the internal energy. Okay, this is one way. The other way is the approximate way, and I'm going to use the approximate way, and most of the time in the course for the compressed liquid table, we're going to use the approximate way. Okay. Now listen carefully. In approximate way, okay, now let's say that you have finalized, that you made a decision that your property should be in the compressed liquid state. So once you have this thing, ignore the pressure. Okay, ignore the pressure and use the temperature value and enter into the saturated table and get the F value for that temperature, and that will be the correct compressed liquid value. Okay, that will be the approximate compressed liquid value. So for example, in this case, you have 6 megapascal 100 degrees centigrade. When we go into 6 megapascal 100 degrees centigrade into the saturation table, now it's very clear that our property is not in the saturation state, it is in the compressed liquid. Okay, so what we can do is that we can get the value of internal energy by saturated table, and this way is the approximate way. Okay, so the thing is that we have to ignore the pressure, and now we have to go into saturated water temperature table and take the U value, UF value, okay, at 100 degrees centigrade. So if we go into saturated water temperature table, and now we need 100 degrees centigrade. So this is saturated water temperature table at 100 degrees centigrade. This is 100 degrees centigrade. Okay, now we are going to take the UF value. So this is the UF value. So it's 419.06, and this UF value could be considered as an approximate value for this problem. So this could be considered an approximate solution. So you don't need to go into the compressed liquid table. You can still stay in the saturation table, but you have to ignore the pressure now. Ignore the pressure. Take the temperature value, and corresponding to that temperature value, find out the F values, and those F values would be considered as an approximate result for the compressed liquid table. So here, for in this case, okay, if you go here in part 5, so at 6 megapascal 100 degrees centigrade, okay, so you can stay in the compress, you can stay in the saturation table at 100 degrees centigrade, take the F value of U, and this 419.06 is the answer. Is this thing clear or not? Let me know.
Yes, sir.
Understand one thing. If you go into the compressed liquid table and you get the value of U there, it will not be the exactly same value. Because this is the reason we are saying this is an approximate method, because there will be some error. The only thing is that as engineer, what we are saying is that the error is acceptable. The error is very small. So we are saying that we don't need to go into the compressed liquid table. We can just directly take the value from the saturation table, but we have to ignore the pressure. Ignore the pressure, take the value from the temperature, corresponding to the temperature, get the value of F values, whether it is UF, VF, SF, HF, but take the F values, and those F values would be considered as the correct value for the compressed liquid. So I have done the solution of this first problem by using the thermodynamic tables. We also discussed about the linear interpolation. Is there anything within the solution of this problem which is not clear? Please feel free to ask.
Understood, sir.
Okay, good. Okay, so let's see this example 2, and inshallah this example 2 will be the last example we are going to cover today. Okay. Determine the enthalpy. So what do we want to find? Enthalpy. Enthalpy means H. Determine the enthalpy of 1.5 kg of water. This is the mass of water contained in a volume of 1.2 meter cube at 200 kilopascal. So we have the mass of water and we have the volume of the container in which water is. So if we have the mass and the volume of the container, so we can find out what is the specific volume, because the specific volume is volume per unit mass. Okay. So divide 1.2 by 1.5, so we have a specific mass of 0.8 meter cube per kg. Okay, and so we have two properties with us. Remember state postulate we discussed in the very first chapter? The state postulate says that if you have two properties, you can find any other property. And this is what we are witnessing here. We need two properties to find all other properties. So one property here in this case is specific volume, and the other property is the pressure. So if we have a specific volume and the pressure, which table should we go now first? Saturated water pressure table, saturated water temperature table.
Saturated.
Water pressure table, because the pressure is given in the question, right? 200 kilopascal. So 200 kilopascal, at 200 kilopascal, we need to now compare V. Okay, so let's go to 200 kilopascal, 200 kilopascal. This is 200 kilopascal. Now at 200 kilopascal, we have the values of VF and VG. Now look at the values of VF and VG. This is VF, this is VG. And what V value that we have? Our V value is 0.8. 0.8 is our V value. What do you think? 0.8 is our V value, and the VF and VG are here in front of you. Are we in the correct table? Should it be saturated state, or should it be superheated, or should it be compressed liquid? Our V value is 0.8.
We are in the saturated region.
We are in the saturation region, exactly. Since we are in the saturation region, okay, now we need to find what is the enthalpy. So for the saturation region, since we compared our value of V with VF and VG, and it is in between VF and VG, so we know that we are in the saturation region. So within the saturation region, now we need to find what is enthalpy. Now for finding the enthalpy in the saturation region, the formula is this: H is equals to HF plus X HFG. The problem is that HF and HFG we can directly find at this pressure, but we need X. First, we need to know what is the quality. Now, the quality is not given, but we can find the quality by using this formula for a specific volume. Because we know what is V, we know what is VF, we know what is VG. We can find what is X. Then use this X in this equation. HF and HFG value we can directly get, because let's see here. So this will be the HF, this will be HFG, this will be HG. Okay, so we have HF, HFG values with us. Okay, and we need to calculate X. X we calculate by using this formula, since we know V, VF, and VG. So we find this and we can find what is the enthalpy. Do you understand the solution here?
Yes, sir.
Good. Okay, example 3 is something you can go through it yourself. Example 4 is something from where we are going to start, inshallah, in the next class. Okay. If anybody want to ask anything, you can ask. Otherwise, our today's lecture is considered over now. Anybody want to ask anything?
No, sir.
No, sir. All good.
So
Yeah, sir.
once again, right now, I need your feedback. Please let me know, are you catching up with me or not?
Yes, sir.
Yes, sir. We are catching up with you.
Good. Anyways, even in case if you feel that there is something I should change in my methodology of teaching, and if you're shy at speaking right now, you can send me a message. Okay, we can discuss things. But important thing is that You need to understand the subject well, and this is my objective. Okay, so if you are catching up with me, good for me. Okay, so that's it. That's it for today. Inshallah, we're gonna meet next week.
Inshallah, sir.
Okay, sir. Allah Hafiz, sir.
Okay, Allah Hafiz.
Allah Hafiz, sir.
Sir.
Officer.
Okay.